Hello and welcome to lesson number 15, applying limits to functions. This is a follow-up video on the last video, which is applying limits. So in this video, we're going to talk about different functions, but we're mostly going to talk about polynomial functions and rational functions. Here, first thing we're going to talk about is polynomial functions. If you don't know what a polynomial function is, click this video in the top right here. So a polynomial function, polynomial, is any function f of x, which is of the form a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus all the way down up to an a1 x to the 1 and an a0 term. So here a0, a1, a2 all the way up to a sub n minus 1 and a sub n are coefficients. All of these are coefficients which are real numbered values. So we can say in general a sub k is an element of the real numbers for all the k's going from n down to 0. And then here this n is an integer. We have an x to the n where n is an integer, so we have an integer power of x. We have one less than that integer power of x. Then we have the next thing, which is also another one less than that integer power, all the way down until the lowest integer power of x to the 1. And then we have an x to the 0 here, of course. This is what a polynomial function is. In the last video, I said that the limit as x approaches let's use some variable here, let's say alpha. The limit as x approaches alpha of f of x, where f of x is a polynomial, is equal to f of alpha for any alpha within the real numbers. So what this means is that the polynomial functions are so well behaved that they are continuous everywhere, well defined everywhere, so we can just substitute the value and that will give us the same value as just putting the limit. So this is the behavior. X of as x approaches alpha, f of x is equal to f of alpha. So here some interesting behaviors of this are what happens when we take the limit as x approaches 0, which is not all that much interesting, but what's more interesting is what happens when we take the limit as x approaches plus or minus infinity. In each of those cases, depending on whether n is an even number or an odd number, different things happen. For now, let's first investigate what happens when we take the limit as x approaches 0 of any polynomial function f of x. So here, what this is the limit as x approaches 0 of all of this stuff on the right, which I'm actually going to copy paste down like this, Control C, Control V, copy paste and put into here. So here what's going to happen is when we apply the limit, all of these x to the n powers will be 0 to the power of n. So this will be 0 to the power n, which is then going to be 0. This is going to be 0 to the power n minus 1, which is going to be 0. So then the whole term goes to 0. The next term is going to go to 0, and so on, all the way down to this term, which is also going to be 0 because this is x to the 1, which is 0 to the 1, which is 0. The only term that survives here is the constant term. So therefore, whatever the polynomial function f of x is, the limit as x approaches 0 of f of x is the constant term. Of f of x. So this should be quite obvious. What might not be as obvious is what happens when we take the limit as x approaches infinity. Here, what I want to illustrate to you is that for this kind of function, the only important values are this coefficient, which is the coefficient of the highest order term, or the leading coefficient. The leading coefficient and the leading term in general is the only thing that matters when we take the limit as x approaches infinity. To show that, first of all, I'm going to rearrange the function f of x. So f of x we had above is equal to this thing right here, which is a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus all the way down to a sub 0. What I'm going to do here is factor out an x to the power of n. So doing that, I'm going to factor out an x to the power of n and write this as x to the power of n times, on the inside, when we divide an x to the power of n here, we have a sub n here plus. The next thing, when we divide out an x to the power of n, we have x to the power of n minus 1 divided by x to the power of n, which is going to be x to the power of minus 1. So this is going to be x to the minus 1, or 1 divided by x. And then there's a coefficient of n minus 1 divided by x plus. The next term is going to be a sub n minus 2. Over here we're going to have x to the n minus 2 divided by x to the n, which is going to be x to the negative 2, or 1 divided by x squared plus, and then we're going to go all the way down up to a sub 1 x to the 1 divided by x to the n, which is going to then be equal to a sub 1 divided by x to the n minus 1, and then plus a sub 0 divided by x to the n. So here you might notice we're dividing by zeros here. It could be potentially x could be 0, but for our purposes it's not an issue, because when we take the limit as x approaches infinity, x is never going to be 0, so we don't have that issue. So I'm going to leave this as is. There is a divide by 0 potential here if we left this as a normal function, but because what we're interested in is the limit as x approaches one of the infinities is not going to be 0, so we don't really care. So now here we can see over here we have an x to the power of n, and it's then being multiplied by all of this stuff in the end. So then if I take the limit as x approaches, let's say, positive infinity of f of x, this is going to be equal to the same limit of the right hand side, which is x approaches positive infinity, which I'll write actually infinity. We'll write positive infinity like this, of x to the power of n multiplied by a sub n plus a sub n minus 1 divided by x plus dot 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 all the way down to a sub 1 divided by x to the n minus 1 plus a sub 0 divided by x to the n. So here what I want you to notice here is that we have a product of two functions. We have a product of x to the n and this other function over here. Recall from the previous video, which I'll link right now. Actually, if you haven't watched that, you should really go watch that. Over here we have one function multiplied by another function. So therefore we can take the limit and break both of them into two separate functions. So this is equal to the limit of the first function, x approaches positive infinity of x to the power of n, multiplied by the limit of the second function. So the limit as x approaches positive infinity of a sub n plus a sub n minus 1 divided by x plus dot 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 all the way down to a sub 1 divided by x to the n minus 1 plus a sub 0 divided by x to the n. So now then, let's evaluate both of these limits separately. On the left hand side, we have a positive infinity to the power of n, and since n is some positive integer, this is a positive infinity to some positive integer power, which means it itself is going to be infinity. If you multiply a really large number by itself multiple times, you're going to still get a really large number. So then if you multiply infinity by itself a large number of times, you're going to get that same infinity. So here what we have is infinity multiplied by and then something over here. On the right side what we have here is the limit as x approaches infinity of all of this stuff. The first term is unaffected, it's just a constant, so we can take it out as a sub n, because remember, again, if you haven't watched the video, you wouldn't know this. Well, you might know it, of course, but if you had watched the video, you would know that the limit of a constant is equal to that constant, so we can take it out. For the next term, we have some constant which is a finite value divided by x, which is an infinite value. Any finite value divided by a really large number as that really large number approaches infinity is going to be approaching 0. We have, let's say this is some finite value, let's say 1. 1 divided by 10 is some number. 1 divided by 100 is a smaller number. 1 divided by 1000 is an even smaller number. As x approaches infinity, this fraction is going to approach 0. Similarly, the next fraction is also going to approach 0 for the same reasons. All of these fractions are going to approach 0. This very last fraction is again a finite value divided by x to the power of n minus 1. This is a positive integer. This is an infinity. So we have 1 divided by infinity format here, which means this is going to approach 0. This last term as well, we have infinity on the bottom, we have some finite value on top, so therefore this is also going to approach 0. So all the terms here are approaching 0 other than this constant term here. So we have this constant term plus a 0, plus a 0, plus a 0, plus a 0 all the way down, plus 0. So here what we have is infinity times a sub n. Now you might directly say this is infinity, right? Well, hold on a little bit. There's a little nuance here, the fact that this could be a negative number. A sub n could be a negative number or a positive number. If a sub n is a positive number, then we are approaching positive infinity, because we have here positive infinity. It's then being multiplied by a positive number, which means we then get positive infinity. However, if a sub n is a negative number, we have positive infinity multiplied by a negative number, which is then going to be negative infinity. So what we have here is the sign and this is not an official thing, by the way, this is just my way of writing it. This has to be interpreted at that given time when you are doing the actual function. I'm just writing it as a general thing. The sign of a sub n, whether it's plus or minus, and infinity. So this could be a plus, this could be a minus. It depends on the sign of a sub n. If a sub n is a positive value, we're multiplying infinity by a positive infinity by a positive value, which means we get positive infinity. If a sub n is a negative value, we're multiplying the negative value by positive infinity, which means we get negative infinity. So that's why I'm putting in symbols here in brackets the sign of a sub n times infinity. In the negative case, we get something else. If we take the limit as x approaches negative infinity of a polynomial, different things happen for different cases. Let's consider again the same exact thing. We're going to consider the limit of f of x, which is then going to be equal to the limit of each of its components. Again here, since we are not taking any values closer to 0, I can write this format where we do in fact have some divisions where this value x could be 0. But since we're going nowhere close to 0, it's alright, we can just substitute that directly. So I'm actually going to copy this thing on the right here, copy it, and bring it down here and paste it in here. I don't need this equal sign. I'm going to cut the equal sign and take everything else, put it, scale it down a little bit, and put it into here. So what we want is the limit as x approaches negative infinity of x to the power of n times this whole thing on the right side. So once again, we can break this into two limits. Here we have a product of one function and another function, which means that since the limit of the product is equal to the product of the limits, provided of course that those limits exist, this is equal to the limit as x approaches negative infinity of x to the power of n multiplied by the limit as x approaches negative infinity of a sub n plus a sub n minus 1 divided by x plus dot 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 plus a sub 1 divided by x to the n minus 1 plus a sub 0 divided by x to the power of n. It's not a sub 6, it's a sub 0. So now then, applying the limits, there's some extra detail that we need to consider here. Here what we have is a very large negative number, negative infinity, taken to the power of n. If n is even, a negative number to the power of n is going to be a positive number. Like let's say negative 2 squared is going to be positive 4. If n is a odd number, however, let's say negative 2 to the power of 3, this is going to be equal to negative 8. You can see here the sign is alternating. If I do another even number, the next even number of 4, negative 2 to the power of 4 is positive 16. So here we can see positive, negative, positive, and then of course negative 2 to the power of 1 is negative 2. You can see negative, positive, negative, positive. If our power, our n, this n here is an even number, then negative infinity to the power of n is going to be a positive number. If not, then it's going to be a negative number. So we have this nuance where in one case one thing happens, in another case another thing happens. So this could either be a negative number to the power of even number, which is going to be positive infinity, or a negative number to an odd power, which is going to be negative infinity. So this could either be plus or minus infinity, we don't know which one. It depends on n. So right now I'm not going to write it, I'm just going to say we'll leave it for later. On the right hand side, however, we can solve this. Over here we have the limit as x approaches negative infinity of first of a constant, then some other terms which have negative powers of x, or 1 divided by x's in them. So here I'm going to leave this thing as it is, and say this is the limit as x approaches negative infinity of x to the power of n in brackets. I'm going to leave it as is, and on the right side we're going to simplify this limit and say the first term here is a constant. The limit of a constant is simply the constant, so we can take that out. The next term here is some constant, some finite value, divided by negative infinity. So once again, if you have any finite value, divide by a big number, you're going to get a number that is very close to 0. Yes, it will be a negative number, but it will still be very close to 0. If we divide 1 by negative 10, we get negative 0.1. If we divide 1 by negative 100, we get negative 0.1. If we divide 1 by negative 1000, we get negative 0.001. So we can see, even though the number is negative, it is getting closer and closer to 0. In fact, in the limit, as x approaches negative infinity, this approaches 0. It approaches 0 from the negative side, provided that a sub n minus 1 is a positive value, and it approaches 0 from the positive side if a sub n minus 1 is a negative value, but still, no matter what, it approaches 0. Similarly, the next term approaches 0 and the next term after that approaches 0. These final terms also, we have a finite value divided by an infinite value, which means we are approaching 0, and this term as well approaches 0. So all the other terms are all approaching 0. Summing them together, we get 0, 0, 0, dot, 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 plus 0. Every single one of the other terms is equal to 0. All we have left is this coefficient here. So now here what we have is that this limit is equal to a sub n times the limit as x approaches negative infinity of x to the power of n. Now we are going to break this into two cases. We are going to break this into the case where n is even and the case where n is odd. So if n is even, one thing happens, and then if n is odd, another thing happens. So if n is even, then we have a sub n here plus, sorry, not plus, times, multiplied by, and over here, this thing is going to be some negative number, some very large negative number, to the power of an even number. As we saw above, any negative number to the power of an even number is going to be a positive number. So here, negative infinity to the power of an even number here is going to be positive infinity. So we have times positive infinity. This case is the same exact case as we had up here, as we saw. And so therefore, the answer we're going to get is that the limit is going to be equal to the sine of a sub n. If a sub n is a negative value, it's going to be negative value times positive infinity, which is negative infinity. Otherwise, if it is a positive value, it's going to be positive value times positive infinity, which is positive infinity. So we have the sine of a sub n times infinity. In the other case, what we have is a sub n multiplied by, and over here, the limit as x approaches negative infinity of x to the power of an odd number is going to be negative infinity, because here we have a negative number, very large negative number. As we saw earlier, a negative number raised to an odd power is going to be a negative number. So therefore, negative infinity raised to an odd power is going to be negative infinity. So here we have negative infinity here. So here, what we are going to have is an infinity. However, since we have a negative here, if a sub n is negative, then we have a negative number times negative infinity, which is then going to be a positive number. So we are going to have a positive infinity. However, if a sub n is positive, then we are having a positive number times a negative number, which is then negative infinity. So this is actually the inverted, the negative times the sine of a sub n infinity. So if the sine of a sub n is positive, then we have negative infinity. If the sine of a sub n is negative, then we have positive infinity. This is what we want to represent here. So be a little careful when you're taking the limit as x approaches infinity of certain functions. If n is even, then of course both sides are going to go to the same thing. We can see this in graphs. The square graph looks like this. The linear graph looks like this. The cube graph would look like this. The fourth power graph would look something like this. We can see for even powered graphs, both infinities are going to the same direction. Over here as well, fourth power is going to the same direction. But the odd powered ones have infinities going in different directions. We can see down, up, down, up. So therefore, if you want to take the limit as x approaches infinity of a polynomial, if it's an even powered polynomial, as in the leading term is an even power, then you can simply just take that infinity and put it multiplied by the sine of a sub n. However, if we have an odd degree polynomial, in which case it is changing. On the positive infinity it's one thing, but on the negative infinity it's a different thing. So therefore, if n is odd, we're going to have different infinities on both sides. So that's all we have to talk about polynomials. Let's now talk about rational functions and their limits. So rational functions are only marginally more complex than polynomials, but we do have to introduce certain terminology when we're talking about the limits of rational functions and the behavior of rational functions in general. So if you don't know what a rational function is, check this video here. A rational function is a ratio of two polynomial functions. So if we say Rx is a rational function, then Rx is equal to Px divided by Qx, where Px and Qx are polynomials. So some integer powers of x are there in the top and the bottom, and they have certain orders and certain behaviors are there, and you'll note here Qx could potentially be 0. So in terms of what this means, what kind of behaviors we can expect, remember earlier in the earlier video when we talked about 1 divided by 0 cases, we found out that when we have 1 divided by 0, if we take the limit as x approaches the value that causes 1 divided by 0, we see that it goes to 1 infinity or another. Either both of them go to the same infinity, one goes to 1 infinity and the other one goes to the other infinity, or that kind of behavior is occurring. So here, when we have Rx is equal to Px divided by Qx, if there are certain values of x for which Qx is equal to 0, at those values we can expect the function Rx to shoot up to infinity. So here that is an important behavior, and the points at which this happens have a special name. They are called vertical asymptotes. Vertical asymptotes. So at a vertical asymptote, the function is discontinuous. There is no actual value at the exact point where the asymptote exists. Rather, on the left hand side we are approaching some infinity, on the right hand side we are approaching some infinity. In the middle at the exact point, there is no exact value. So over here, for examples of a vertical asymptote, we can take y equals 1 divided by x. This function has a vertical asymptote at x equals 0, as we saw earlier last video as well. When you draw out this function, on the right hand side it looks like this, on the left hand side it looks like this. At x equals 0, there is no value, it's undefined, because we have a 1 divided by 0 at this point. On the right hand side to this point, we have 1 infinity approaching. On the left hand side we have a different infinity. It could have also been the same x infinity. For example, if we had, instead of 1 divided by x, if we had 1 divided by x squared here, the graph would look like this. Still, at x equals 0 we would have an undefined value. To the right hand side we have an infinity, and to the left hand side we have an infinity. This right here is a vertical asymptote. So graphs can have multiple vertical asymptotes, and the number of vertical asymptotes is equal to the number of roots that the function on the denominator has. So vertical asymptote, if we say in general, is, I'll write it as a point where Rx approaches infinities. It doesn't have to be the same infinity on the left and the right, it just has to be some infinity on the left and some infinity on the right relative to some point, and at that point of course the function is undefined. So this happens when, I can put like a IE here, when Qx is equal to 0. So for all the values when Qx is equal to 0, we will have a vertical asymptote for a rational function in the form Px divided by Qx, where Px and Qx are polynomials. So we can use this knowledge to estimate the number of vertical asymptotes we could possibly have. It is possible that we have some potential roots that are complex roots, in which case they will not appear in the real numbers, so we will have less than that. But if Qx, we can say that in general, if I'll write some definitions here, we'll say that Px is order n and Qx is order m, then there will be at maximum m number of vertical asymptote, because as you might recall, if we have a polynomial of degree n, the maximum number of roots it can have is n number of roots. So here we can say at maximum we will have at maximum m number of vertical asymptotes. It is of course possible for us to not have any vertical asymptotes at all. If Qx does not have any solutions as Qx equals 0 within the real numbers, then we will never have a vertical asymptote within our rational function. So that's that behavior of Qx. Qx determines where we have vertical asymptotes. There's another thing within these rational functions, something called a horizontal asymptote, but it requires a special condition to happen. Before we discuss that, we are going to first consider what this function does when we go to infinity. And there are three cases that we have to consider here. When considering limits as n approaches infinity, x approaches infinity, we need to consider the cases where n is less than m, n is equal to m, and n is greater than m, i.e. the cases where the denominator has a higher order, the numerator and denominator have equal orders, and the numerator has a higher order than the denominator. So for the first case, if we have this thing, we have some behavior like this. If we take what Rx is, Rx is going to be equal to, let's say, a sub, we'll say a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus all the way down to a sub 1 x to the 1 plus a sub 0, a sub 0. And on the denominator, let's say we have the coefficients of the denominator represented by b. So this will be b sub n x to the m plus b sub m minus 1 x to the m minus 1 plus dot 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 all the way down to b sub 1 x to the 1 plus b sub 0. So this is the general form of the polynomial, the rational function Rx in terms of the numerator's polynomial and the denominator's polynomial. In the first case, when n less than m, if I factor out x sub m from both of these, if I just take an x sub m out of the denominator and the numerator, then what we're going to have is that Rx is equal to x to the power of m, and then divide by x to the power of m times and times something. So over here, from the numerator, if I factor out an x to the power of m, we're going to have, when we divide an x to the power of m here, we're going to have x to the power of n minus m times a sub n. So I'll actually write a sub n x to the power of n minus m. The next term here is going to be a sub n minus 1 times x to the power of, here when we divide by x to the power of m, we're going to have x to the power of n minus 1 minus m. So we're going to have x to the power of n minus m minus 1 plus dot 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 all the way down. The very last terms we're going to have are a sub 1 x to the power of, here we're going to divide by x sub m, x to the power of m, which means we're going to have x to the power of 1 minus m. Plus the last term, which is going to be a0, I'll take a little bit of space because I've actually run out of space within this bracket, a sub 0 and then x to the power of negative m. And then on the denominator, similarly, we have another factorization we need to do. If we start factorizing x to the power of m's out, over here we have b sub m x to the power of m, taking an x to the power of m out, we have just b sub m. Plus, the next thing here is going to be b sub m minus 1. And then dividing this by x to the power of m, we have x to the power of m minus 1 minus m, which is going to be x to the power of negative 1. So I'm actually going to write that as x to the power of negative 1. Plus, dot dot dot, a bunch of terms in the middle. The last term is going to be b sub 1 x to the power of 1 divided by x to the power of m is going to be x to the power of 1 minus m. Plus, and then last term is going to be b sub 0. So this is all we have here. Now, I'm going to take the limit of both sides and cancel out this x to the power of m. I can cancel out the x to the power of m and not have an issue here because x is not equal to 0, because we are considering the limit as x approaches infinity. So here, if we do that, taking the limit of both sides as x approaches, we'll do positive infinity first. X approaches positive infinity of Rx is going to be the limit as x approaches positive infinity of all of this. Copy and pasting all of this down by Control C, Control V this. I'm going to have to shrink it a little bit because it's too big. Put it here. Over here, what we have is some powers on top, some powers on bottom of x. Over here, for the first case, since we considered n less than m, n minus m is a negative number. N minus m minus 1 is a negative number. In fact, all of these powers here are negative numbers. On the bottom, we have x to the power of 0 here, we have a negative number here, negative number here, negative number here. Actually, I missed one. Negative m here. All of these powers of x are negative numbers. This is the only term on the denominator with a non-negative x to the power of 0. All of these powers here are negative. So then, if we spread this limit, remember limit of one function divided by another function is the limit of the first function divided by the limit of the second function, provided that the limit of the second function is not equal to 0. So then taking the limit here, this is equal to the limit of the top function as x approaches positive infinity of the first function divided by the limit as x approaches positive infinity of the second function. So the first function is all of the stuff inside of the brackets, which I'll copy paste down. This is all of this. Control C, Control V, bring it down here. You can remove this bracket. And the bottom function is all of this, which I can again copy paste down and bring it over here. I've seem to have missed a few symbols when I'm copy pasting, so I'll write those in. X to the power of 1 minus m, and here x to the power of negative m and b0. So then, if we consider what's happening here, all of these powers are negative. So we have 1 divided by x's over here, 1 divided by x to some power which is greater than 0. So then, if we substitute positive infinity into each of these, we're going to have this thing approaching 0, this thing approaching 0, all of the stuff in the middle approaching 0, and the very last term as well approaching 0. So here, everything on the top is approaching 0. So then the whole thing on top is equal to 0. So we have equal to 0 on top and something on the bottom. On the bottom, here this is a constant. Taking the limit of a constant is same as the constant. So we have just bm here plus over here. This is a negative power of x. Every other term here is also going to be a negative power of x all the way down, and then taking the limit as x approaches positive infinity of all of these negative powers is going to make all of them approach 0. So this is approaching 0, this is approaching 0, this is approaching 0, this is approaching 0. So everything else is approaching 0. If I write them down, plus dot dot dot, all of them are 0. So we have 0 divided by b sub m. If b sub m is the leading term, then that means that b sub m cannot be 0. So therefore we have 0 divided by a non-zero value, which means we have just 0 here. So therefore the limit as x approaches positive infinity of a rational function where the numerator has a lower power than the denominator, or the order of the numerator is lower than the order of the denominator, is going to be equal to 0. Meaning when we make x very big, if the order of the top is lower than the order of the bottom, then we are going to have equal to 0 on the right hand side. We need to do the same thing on the left hand side, of course. We need to take the limit as x approaches negative infinity of the same exact thing. X approaches negative infinity of the same exact thing. Since nothing else changes, like when we are simplifying this limit stays until the final step where we actually substitute. I'm actually going to skip a few steps and say that the limit as rx of x approaches negative infinity of rx is equal to the limit, and I'm actually going to copy paste the whole thing we had up here before we apply the limit, and then simply apply the limit. So here every simplification step we did up to this point is going to be there in this other thing that we want as well. It's only with the final step where we substitute the actual limit that changes here. So here the same exact stuff applies, and over here what we have is the limit as x approaches negative infinity of the numerator divided by the denominator. Taking these things out, we can take the limit of the numerator divided by the limit of the denominator and say that this is equal to the limit as x approaches negative infinity of the first thing divided by the limit as x approaches negative infinity of the second function. The first function is going to be a sub n x to the n minus m, which is a negative number here, plus a sub n minus 1 x to the n minus m minus 1, plus dot dot dot, plus a sub 1 x to the 1 minus m, plus a sub 0 x to the negative m. All of these powers on the numerator here are negative numbers because recall n itself is less than m. So n minus m is negative. Here we have numbers that are less than n minus m, so these numbers all should be negative. On the denominator what we have is b sub m x to the 0 plus b sub m minus 1 x to the negative 1 plus dot dot dot, plus last thing we have is b sub 1 x to the 1 minus m plus b sub 0 x to the negative m. Here all of the powers of x except for this first power are all negative. Now applying the limit, on top what we have is some coefficient which is finite times x to the negative power where x approaches negative infinity, 1 divided by any infinity, whether it's positive or negative, is going to approach 0. So therefore this term is going to approach 0. Similarly, the next term, which is also a negative power, is going to approach 0. Every other term is also going to approach 0. So all of these terms are going to approach 0, meaning that the entire sum on top is going to approach 0. So therefore we have 0 on top when we take the limit. On the bottom, what we have is the limit of a constant, which is just the constant. So b sub m down here, plus this thing, which is a negative power, which means as we go x to negative infinity, the negative power is going to give us 1 divided by infinity, which is going to give us 0. So this is going to approach 0. The next term has a lower power, so it's going to approach 0. And all the other terms are also going to approach 0. So every single term here is approaching 0 except for this constant term. So we have plus 0, plus 0, plus dot dot dot, plus a bunch of zeros. So here we have 0 divided by bm once again, and here since bm is the leading coefficient, it cannot be 0. So we have 0 divided by a non-zero value, which means we have 0 here. So therefore in this case as well we have 0. Meaning that given that n is less than m, meaning that the numerator in our rational function has lower order than the denominator, given this will say that the limit as x approaches either the positive or negative infinity of r of x is going to be 0. No matter what we do, approaching positive infinity or negative infinity, if the numerator has lower order than the denominator, then as we send x to infinity, r of x is going to approach 0. So that's what we mean here. We're going to write this as a statement and say that in the case that n is less than m, meaning the numerator has lower order than the denominator, our rx is going to approach 0 as x approaches either positive infinity or negative infinity. The next case we are going to consider is the case where the numerator and denominator have equal orders. In that case, we can write rx as something like this. If rx is a rational function where the numerator and denominator have equal orders, then rx will be on top some a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 plus dot 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 all the way down to a sub 1 x to the 1 plus a sub 0. On the denominator, since m is equal to n in this case, since we have m and n equal to each other, meaning that the numerator and denominator have the same order, the denominator we could write as b sub n x to the n. It's the same exact thing as writing b sub m x to the m in this case, because m is equal to n. The next term we are going to have here is going to be b sub n minus 1 x to the n minus 1 plus dot 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 a bunch of terms, and then b sub 1 x to the 1 plus b sub 0. Now the strategy we are going to do is again factorize out the highest thing here, x to the n, from the top and bottom, in order to get a constant term here, and you will see by consequence we are also going to get a constant term here. So let's do that. If we take the top, factoring out an x to the n, what we have left is an a sub n plus the next term is going to be a sub 1 x to the negative 1. So a sub n minus 1 x to the negative 1, which I'm going to write as 1 divided by x, plus the next term is going to be a sub n minus 2 divided by x squared plus dot 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 all the way down until we get to a sub 1 divided by x to the n minus 1 and a sub 0 divided by x to the n. On the denominator, what we are going to have is, when we factor out an x to the power of n, we are going to have b sub n plus b sub n minus 1 divided by x plus b sub n minus 2 divided by x squared plus dot 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 all the way down up to b sub 1 divided by x to the n minus 1 plus b sub 0 divided by x to the power of n. So now here, since the limits we are interested in are non-zero limits, we are not interested in x equals 0, we are interested in x going to infinity, we can actually cut both of these. Because here x is not equal to 0, so the x to the power of n is also not equal to 0. Now then, we have r of x is equal to this function divided by this function. That means that the limit as x goes to, first we will check positive infinity, of r of x is going to be equal to the limit as x approaches positive infinity of the first function divided by the limit as x approaches positive infinity of the second function. So substituting these in, the first function is a sub n plus a sub n minus 1 divided by x plus dot 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 plus a sub 1 divided by x to the n minus 1 plus a sub 0 divided by x to the n. On the denominator what we have is b sub n plus b sub n minus 1 b sub n minus 1 divided by x plus dot dot dot. Finally b sub 1 divided by x to the n minus 1 plus b sub 0 divided by x to the power of n. Now, taking the limits of the top and bottom here, on top we have just a constant of a sub n. So that thing is going to be left alone, it's going to be a sub n. Plus, and there's a bunch of stuff. Over here, the next thing we're going to have is a sub n minus 1 divided by x. Here, since x is approaching infinity, this is going to approach 0. The next term after that is also going to approach 0. All of these terms here are going to approach 0. So then what we have is a sub n plus 0 dot 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 plus 0. On the denominator, if we look, we have a constant term here, which means it gets preserved, plus, and then over here the next term is divided by x, so it's going to go to 0. Next term after that's going to 0. All of these terms are going to 0 because x is approaching positive infinity. So then again we have 0 plus dot 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 all the way down plus 0. So then cancelling out all of the zeros and leaving them alone, what we are left with is a sub n divided by b sub n, and since a sub n and b sub n are non-zero, we can say that this is some finite value because a sub n and b sub n are the leading coefficients of the numerator and denominator respectively. So then, as x approaches positive infinity, when the order of the numerator and denominator are equal, we have that, I'll actually write that, when n equal to m, we have that the limit as x approaches positive infinity of Rx is equal to a sub n divided by b sub n, where a sub n and b sub n are the leading coefficients of Rx, Rx's numerator and denominator. Next, we have to consider the negative infinity case, and I'm not going to do that all the way. I'm just going to go until the point where we apply the limits. The limits as x approaches negative infinity of Rx, it's actually going to give us the same exact result, which is why I'm not going to put in the effort to it. I'm going to simply copy this thing down and write the same exact thing, except I'm going to swap the two limits. So I'm going to copy this down to here. This is this, and then all I'm going to do is swap the two limits, and you'll see it's actually the exact same thing, equal to this. So here, instead of positive infinity, what we have here is negative infinity. Removing the two positive signs here, replacing them with negative signs, we can see that as we have the limit as x approaches negative infinity on the top and bottom, still we have a constant here, which means it gets left alone. On the denominator as well, we have a constant, which means it gets left alone. A sub n and b sub n are left alone. All the other terms have a divide by x, meaning even though we're taking negative infinity, it's still going to approach 0. All of these terms approach 0. All of these terms approach 0. So this is just 0 plus 0 dot 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 all the way down plus 0. On the denominator as well, we have plus 0 all the way down plus 0. So then again the answer is a sub n divided by b sub n. So we can see in the negative case as well, we have that as x approaches negative infinity, the limit of x approaching negative infinity of Rx is equal to the leading coefficient of the numerator divided by the leading coefficient of the denominator. So we can write in general, in the case where I'll actually have to put that as a star, when n equals m, this means that the limit as x approaches either the positive or negative infinity, both of them do the same thing, of Rx is equal to a sub n divided by b sub n, where a sub n and b sub n are the leading coefficients of the numerator and denominator of Rx respectively. Next, of course, the final case that we have to consider is the case where the numerator has greater order than the denominator. So we have to consider the case where the numerator has a greater order than the denominator, i.e. when n is greater than m. In this case, writing Rx out, Rx is equal to, and I'm actually going to not waste your time or my time, I'm going to go up here and copy paste what I wrote up here because it's the same exact thing. We have this thing, copy, bring it down, except now n is greater than m. So what does this mean for us? Well, since over here n is greater than m, it means that x to the power of n is a greater power than x to the power of m. So then let's try and see what happens if we try to factor out x to the power of n from the top and bottom as well. If we try to do this, what we have on top is x to the power of n times some function, and on the bottom what we have is x to the power of n times some function. So factoring this out, on top what we get is a sub n plus over here we have x to the power of n minus 1. Dividing it by x to the power of n, we get a sub n minus 1 times x to the minus 1, which I'm going to write as 1 divided by x plus all the other terms will have negative powers of x. I'll actually write the next one. This is n minus 2 divided by x squared plus dot dot dot. The last term is going to be a sub 1 divided by x to the power of n minus 1, and the term after that is going to be a sub 0 divided by x to the power of n. On the numerator, that's what we are going to have. On the denominator, we are going to have b sub m and then x to the power of m divided by x to the power of n, which is x to the power of m minus n, which is a negative number since n is greater than m. And then the next term we are going to have is b sub m minus 1 times x to the power of m minus n minus 1, which is still negative since it is less than m minus n, and m minus n in itself is already negative. And then we have a bunch of terms in the middle, and then the last term over here is going to be b sub 1 x to the power of, and here we have 1, and then we have negative n, so we have 1 minus n, and then the last term is going to be b sub 0 x to the power of negative n. So all of these powers over here are all negative. All of the powers except for the first thing over here are all negative. Now we can also of course cancel out these two x to the power of n's here, because x is not 0 for the limits we are going to be considering. And now we can consider the limit as x approaches. First we'll do positive infinity of rx on the left. This is going to be equal to the limit of the top divided by the bottom. So we have limit of x approaches positive infinity of the top divided by the limit as x approaches positive infinity of the bottom. So on top, on the numerator, what we have is a constant a sub n plus, and then a sub n minus 1 divided by x plus a bunch of other terms with negative powers, and the very last term, which is a sub 1 divided by x to the power of n minus 1 plus a sub 0 divided by x to the n. On the bottom, what we have, if I should have kept it consistent and written the denominator as well in that format, which I'll do now. This is b sub n divided by x to the power of n minus m plus b sub m minus 1 divided by x to the power of here n plus 1 minus m plus dot 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 all the way down until the very last term of b sub 1 divided by x to the power of n minus 1 plus b sub 0 divided by x to the power of n. So now taking these limits on top, first thing we have is a constant of a sub n. This thing stays as a sub n. The next term is going to be this thing, and that's going to be approaching 0. The next term here is going to be approaching 0. All of these terms here are going to be approaching 0. So we have plus 0, 0, 0, 0 all the way here. On the denominator, however, what we have is a bunch of terms which are all approaching 0. So this entire thing, this is approaching 0, this is approaching 0, this is approaching 0, this is approaching 0. So what we have is a bunch of terms that are all approaching 0. So I'm going to not say equal to 0, I'm going to say approaching 0. So since the denominator is approaching 0, we can say this whole thing is going to approach infinity. This whole thing is going to approach infinity. Which infinity is going to approach? Well, that all depends on the sign of a sub n. Because here we have one infinity here, so 1 0 here, we have another 0 here, here we have a sub n, so we have infinity basically multiplied by a sub n. So it depends on the sign of a sub n. Similarly, if we apply the negative limit, I'm not going to waste your time with that one because it's the exact same thing except that we swap the signs. As x approaches negative infinity, rx is equal to, and then here I'm going to copy the exact same thing because of course as we saw in the previous two examples, nothing changes in between these two, so we can copy paste this directly and write the exact same thing, except now we have negative signs. So here we have the limit as x approaches negative infinity in this case. Now here same thing, we had a limit as x approaches negative infinity. Still all the 1 divided by x's and 1 divided by x squareds and all of that is still going to be approaching 0. So all of this stuff is still approaching 0 and all of this stuff is still approaching 0. The only thing we have here is the a sub n here, which means that still this whole thing is going to be approaching a sub n multiplied by some infinity. So again, which infinity it is depends on the signs of the coefficients that you have in your two functions. But we can see if we have the limit as x approaches plus or minus infinity of rx in the case where n is greater than m, then this thing diverges. It does not go to a finite value, it instead goes to infinity. So we can say as a general theorem, if we have a rational function where the numerator has higher order than the denominator, we have a divergent function. As we go x approaches infinity in the plus or minus directions, we are going to be approaching some infinity. In the other cases where where we have n is equal to m, as x approaches plus or minus infinity, the ratio is a sub n divided by b sub n. And in this case up here, where n is less than m, meaning that the order of the numerator is lower than the order of the denominator, doesn't matter which plus or minus infinity we go to, the limit as x approaches plus or minus infinity of Rx is going to be equal to 0. So here, in this case, the case where n is less than m and the case where n is equal to m will have us approaching some value as we get larger and larger x's in either the positive or negative direction. This will look like something like this on the graph. If we draw the graph of this rational function Rx, something weird will happen in the middle. We'll not mess with that, something weird is happening in the middle. But towards the ends, for the case where n is less than m, no matter what the function is doing, as we get really large x's in the positive or negative direction, we're going to be approaching 0. So on the right side it will look like this, on the left side it will do something, and then it will look like this. This is not representative of what actual rational function does, by the way. This is just to indicate that there's something happening here, but it doesn't really matter for us in this context, because all I'm talking about is what happens when we get really big x's in the positive direction and really big x's in the negative direction. In both of these cases, the value of Rx is going to be approaching 0. This is what we call a horizontal asymptote. The horizontal asymptote is the value that we are approaching as we get really large x's. So here, another terminology, the horizontal asymptote. This is the value that we approach as x approaches infinity in the cases where n is less than m, and in the second case which we are going to see, when n is equal to m. When n is equal to m, there's only a slight difference. Again, if we draw the graph of this rational function where n is equal to m, we have something messed up in the middle which I'm not going to draw. I'm just going to represent it with some scribbly lines. And over here, instead of our function approaching 0 when we have really large x's, instead our function is going to approach some non-zero finite value. So something like this. On the left side as well, it will look something like this. It could also be coming from the upside as well. It could be something like this, of course. But on the left side and the right side, our function is going to be approaching some same finite value, which, if you recall, is going to be a sub n divided by b sub n. So here in this case as well, we have a horizontal asymptote. In the above case, when n is less than m, the horizontal asymptote is at y equals 0, but in this case, where we have n equal to m, we have a non-zero finite horizontal asymptote, and it's going to be at y equals a sub n divided by b sub n. So that's what horizontal asymptote is. In questions in practice, you will see this kind of thing. We'll take a look at one practical question from some A-level paper and conclude this lesson for today. For right now, we learnt about polynomial functions as you take the limit as x approaches infinity. We also briefly discussed what happens when x equals 0. It's very simple, it's just the coefficient of the constant term. And then we discussed what happens when you have a rational function. When you have a rational function, the behavior is much more complex, because in a rational function, the numerator can be one value, the denominator can be another value. The denominator could be 0, in which case we have something called a vertical asymptote, and there can be a maximum of m number of vertical asymptotes, where m is the order of the denominator. Furthermore, we discussed what happens when we send x to infinity. This happens in multiple different ways depending on the relationship between n and m, where n is the order of the numerator and m is the order of the denominator. When n less than m, we saw no matter which infinity you send your function to, it is going to approach 0. In the case where n is equal to m, we saw that when you send your x to some infinity, you get the ratio of the highest order term's coefficient, or the leading coefficients of the numerator and the denominator. And in the case when n was greater than m, meaning that the numerator had greater order than the denominator, we saw that the limit as x approaches positive or negative infinity of Rx is divergent. It approaches some infinity. And then we discussed what happens in the two cases where n is less than m and when n is equal to m. In these two cases, we are approaching some horizontal value, some vertical maximum, some vertical finite height. When n is less than m, this height is x equals c, y equals 0. So we've drawn here, we have a horizontal asymptote at y equals 0. And in the case where n is equal to m, we have a horizontal asymptote at some non-zero value of a sub n divided by b sub n. Let's now look at a practical example of where this kind of knowledge will be used in a paper. So here's one simple question. It's from the 2022 A-level combined mathematics paper 1, question number 14. We're not going to do the whole part of question number 14, of course, because that's a large question and it includes theories that have not been discussed yet. But what we're going to do is consider this statement given, and we're going to find the horizontal and vertical asymptotes of this function given here. So we have, let fx equal 9 x minus 2 squared divided by x squared for x's not equal to 0. The reason for x not equal to 0 is of course because when x is equal to 0, we have divide by 0 occurring here. Since we want to avoid divide by zeros, as at those values fx is undefined, we simply cut that out of our possible domain. So for x not equal to 0, any other x in the real numbers, fx is equal to 9 times x minus 2 squared divided by x squared. Here we can see on top we have x minus 2 squared, which is an order 1 polynomial squared, which is then going to give us an order 2 polynomial. And then it's multiplied by constant 9. On the denominator what we have is simply an order 2 polynomial x squared. So rewriting this a little bit, fx equal to, squaring the inside we have 9 times x squared, and then x minus 2 squared is x squared minus 4x minus 4, so plus 4. So therefore we have 4 times 9, which is negative 36x, and then plus 36 divided by x squared. This is the simplified version of our function, of course, for x not equal to 0. In this case, in this representation, we can see top we have order 2 polynomial, bottom we have order 2 polynomial. So therefore, if we consider limit as x approaches plus or minus infinity, this is going to be equal to the leading coefficient of the first thing divided by the leading coefficient of the second thing. So leading coefficient of the first thing is going to be equal to 9 divided by the leading coefficient of the denominator is going to be 1. So 9 divided by 1 is equal to 9. So therefore, our horizontal asymptote as x approaches plus or minus infinity, we are going to have a horizontal asymptote at y equals 9. So you'll see if you actually draw the graph, which I'll put an image right now. If you draw this graph, you will see at x equals positive and negative infinity, the graph is approaching y equals 9. How about vertical asymptotes? Well, the only place where a vertical asymptote can occur is if the denominator becomes 0. In this case, the only way that the denominator can become 0 is if x itself is equal to 0. So therefore, we can see at x equals 0, we're going to have a vertical asymptote. Now note, even though the order of the denominator is 2, we have only one vertical asymptote. That's because in this case, we have the denominator being a repeated root, as in x equals 0 and x equals 0. This is because x squared is equal to x times x, and which is then equal to 0. So therefore, this x could be 0 or this x could be 0, which means what we have here is the same repeated root again. So here, note, this is reflective of what we talked about. We talked about the fact that the number of vertical asymptotes that you have is going to be less than or equal to the order of the denominator. In this case, it's less than. Even though the order of the denominator is 2, we have only one vertical asymptote. That vertical asymptote is at x is equal to 0. So we have a vertical asymptote at x is equal to 0. Now within the question, you are expected to write some proofing for this. So in this case, what we would write, this is what you would require in order to write this thing. But in the other case, for the vertical asymptote, you would have to write something like the limit as x approaches 0 from the positive direction of fx is equal to something, and then similarly the limit as x approaches 0 from the negative direction of fx is equal to something, compare these two and find it. In this case, since the order of the numerator and denominator are both even, we have that we simply have to multiply the power of the sign of the coefficient on the front by infinity in order to get where this is going. So in this case, since the coefficient is 9, as in positive 9, we have to multiply positive 9 by positive infinity, which gets us positive infinity in both the positive case and negative case as we approach 0. So we have plus infinity in both of these cases. So therefore, the limit as this rational function fx approaches 0 from the right side and left side is going to be positive infinity. Therefore, the limit as x approaches 0 of fx in general is going to be positive infinity. Therefore, we have a vertical asymptote at x equals 0, where at that point fx is going to be approaching positive infinity from both directions. Again, here's the graph of the function. You can see this is also holding up. So that's it we have for the limits applications within what we've discussed so far. When we learn more, we'll be able to apply our newer knowledge into questions later, but for now, this is all we have. So that's it. Thank you for watching this lesson, and goodbye.